Our routers have what is known as an output queue. Now, what is the output queue? It's a place in memory that our routers can store those packets that they have to forward out a particular interface. So it's just a holding place, a holding cell, if you might say, for those packets that are going to be transmitted. Now, the queue is only a certain size, and that queue can fill up. And when that queue fills up, our networks experience congestion because traffic that's arriving at the router is faster, more abundant than the traffic leaving the router. So there's more packets arriving than we are able to transmit out that interface. Now, what happens by default on our routers in this particular case? Well, we can see here that our software queue is full. Our complete queue is filled with packets. The new packets that are arriving can't fit into the queue on the interface. So what does the router do? Well, the router has to drop them. Sends them into a big bucket. This is known as tail drop, and it's the default behavior of our routers. But this can cause some serious issues within our organization. Serious issues. For example, with tail drop, we could have what is known as global synchronization. What's global synchronization? Well, global synchronization occurs when all of our end stations synchronize the TCP flow control features, the slow start process, and their window sizes. That's right. Now, how in the world can devices that are not even communicating with each other synchronize on a global level all of their TCP sessions? Well, let's look at this. Let's say we have 3 PCs, all of them with different flows. So flow A, flow B, flow C. And we have routers and switches in our network. We have our PCs sending their traffic. Notice here what happens. We have an abundance of traffic being sent, and then all of a sudden we're experiencing tail drop. When we experience tail drop with TCP, what is going to happen? Well, those segments that are being sent by our PC get dropped. So that means they are not acknowledged. Well, there's a retransmit timer. And what'll happen is that our PC, the sender, will retransmit after a certain period of time that particular TCP segment. But with the overall process of TCP, since we have segments that are going unacknowledged, we back off. What does that mean? We send less information. So we send less information, and that decongests the network. It decongests the network. It clears things up. So then we start to slowly grow our window size and the amount of information we're going to send. But notice here that our other devices in the network are also sending information. So they start sending and they start growing. We all start growing, and then boom, we all experience what? The congestion at the same time, and then tail drop. We all back off at the exact same time. Because what? Our segments are getting dropped. They're going unacknowledged. So we back off. We slowly increase the amount of data being sent. And then, boom, we all experience that dropping of segments at the exact same time. This is global synchronization. Everybody's TCP sessions are synchronized. They're restarting at the same time. And this is all because of tail drop. So we're going to have these periods of time in our network where traffic, everything's fine, and lots and lots of congestion, everybody backs off, things are slow, things are good. Oh, and then things are slow. You see that? You see that? It's just this constant wave of great, bad, great, bad, great, bad, great, bad. And it's something you want to be familiar with. Now, we can prevent this from happening by, or not prevent it, but reduce the likelihood of it happening by simply changing the way that our routers behave. So instead of using tail drop, we could use, for example, weighted random early detection, WRED instead. And the likelihood of this happening is significantly reduced at that point in time. In addition to the global synchronization issue from tail drop, we can also have TCP starvation. Also, there is no way to differentiate the different traffic. So what does that lead to? It leads to delay for TCP traffic, jitter for traffic, and the overall starvation, as we just mentioned. So look at the queue again. The queue is full. And when we have extremely high buffer usage, meaning that the queue is full, and that means we have a long queue, it causes delay. Why? Because traffic's sitting in the queue for a relatively long time. Notice that we have some blue traffic. This is going to be our UDP traffic. And then we have our green packets, which is going to be our TCP traffic. Notice that the precedence, the IP precedence of our TCP traffic is 3, and our UDP traffic is 0. So which one should have a higher priority? Well, the higher priority is the TCP-related traffic. But is it getting priority? No, it's not, because tail drop does not look at IP precedence. So since tail drop's not looking at IP precedence, our packets are getting dropped. Which is going to cause what to happen? Well, our global synchronization, our TCP restarts and resets and all that fun stuff. Then we have that global synchronization. So these more aggressive flows, these UDP flows, are starving out TCP. That's what they're doing here. They're starving out TCP. So all of those TCP packets are going to the bit buckets.